Okay, so today we're going to start out talking about chemical reactions. And moving forward, that's what we're dealing with, chemical equations, chemical reactions. So let's talk about chemical reactions for a little bit. So before we do that, we need to get into talking about something that we learned a little bit about way back at the beginning of the course. So if you remember, John Dalton's atomic theory had those 5 parts of the atomic theory, his 5 postulates. One of them was that in a chemical reaction, elements are combined, separated, or rearranged to form new compounds. That was one of his 5 postulates to his atomic theory. Now, in that he says no new matter is formed. What that means is matter is also not destroyed. So nothing new is formed and nothing is destroyed. All that's happening is the chemicals that are involved are rearranging themselves when we have ourselves a chemical reaction. So all matter that was there before the reaction is still there after the reaction. That is a very important concept. So mass, when we're talking about mass, it's a measure of the amount of matter in a sample of the substance. So if matter is conserved, all the matter that was there before, then that means the mass is conserved. Because if all the matter that was there before is there after, then whatever the mass, the measurement of how much matter was there, how much matter is there before, it's going to be the same as what's there after. It kind of makes sense. Mass is a measurement of the amount of matter, so the matter there before means that the matter thereafter also means that whatever mass was there before has the same mass as after. So matter and mass are both conserved. So what does conserved mean? It means constant. It means the same before and after. It's a numerical thing. The amount of something you had before the reaction is going to equal what happens or what you have after the reaction. That is what we mean by conserved. There are lots of laws of conservation in science. So it doesn't really matter what quantity we're discussing. If it says it stays the same from beginning to the end, we're dealing with a law of conservation. I mean, there's law of conservation of energy, law of conservation of mass, conservation of charge, conservation of momentum. There's lots of laws of conservation in science. The one we're going to deal with the most is this one, the law of conservation of mass. That's the one that matters the most to chemists. It's the conservation of mass. The mass before the reaction equals the mass after the reaction is basically what it says. So the isolated closed system, the total mass of the system will remain unchanged. Closed, isolated system. The total mass of the system will remain unchanged. So what does that mean? Well, a closed system is a system in which matter is not able to leave or enter the system. So it's contained, it's closed. You can't add stuff to it and stuff can't escape out of it. A closed system, matter is not able to leave or enter the system. An isolated system deals with energy. We can't have energy coming in or leaving. So whatever energy is there before and whatever energy is there after, it's not coming or leaving the system. So a closed, isolated system, it's very specific qualifications, by the way. For the law of conservation of mass to occur, you have to have a closed, isolated system. Most actual reactions do not occur in a closed, isolated system, unless, of course, we're talking about the system as the entire universe. The entire universe is a closed, isolated system. But in most lab situations, we're not dealing with a closed, isolated system. In lab, we can create a situation in which we have a closed and isolated system, but it's not the typical way that things happen. So we have discovered this law by creating a closed, isolated system. But just realize that the reason not everything always works out perfectly in a chemistry lab is because we don't actually have a closed, isolated system. We can get really close in a lot of cases. We can based off the equipment that we're using, we can make it to where it's a little bit better, but we can't actually get to a perfect closed, isolated system in most situations. So our numbers are never going to work out exactly correct, but they're really, really close. That's what we call experimental error, and that's why we deal with experimental error, and we'll talk about that a little bit more later. So when we do keep things as close to a closed isolated system as we can, we see that the mass is conserved. The mass before a reaction and the mass after reaction is the same, which means the mass is conserved. And so we have validated and upheld this law of conservation of mass. So we have to remember the total mass before a reaction must equal the total mass after the reaction. So the mass of your reactants has to equal the mass of your products. The total mass of reactants equals the total mass of the products. Okay, so what are our reactants and products? Reactants are the compounds or elements that are present in the system before the reaction and the ones that participate in the reaction. Sometimes you'll have a lot of other things that are there, but they're not actually part of the reaction. So they're not considered reactants. They're what we call spectator chemicals. They're there, they are just there. They're not actually part of the reaction. So the reactants are the chemicals that are there and part of the reaction. The products are compounds or elements that are newly formed in the chemical reaction, not created out of nothing, but newly formed compounds or newly released elements. So as we're dealing with this, again, they're just rearranging themselves. So if I have carbon dioxide before the reaction, that's made up of carbon and oxygen in a compound, but then afterwards I have carbon and oxygen separated, then they're now elements when before they were compound. And so it's a newly formed product, but it's not something that wasn't there before. The carbon and the oxygen were there before. They were just combined inside of a compound, and now they're separated. So products are the things that are produced whenever the reaction takes place. So let's look at an example of how this law of conservation of mass works. So if I have 25 grams of reactant A and I combine it with 45 grams of reactant B, I'm going to get the products of the reaction, or two new compounds, product C and product D. So chemical A and B combined and they produce chemical C and D. Now if I measured 50 grams of product D, what product C should I expect? So I started with 25 grams of A and 45 grams of B, and I end up with 50 grams of D. So how much C should I get? How much C should I have? Well, the total mass before has to equal the total mass after. So doing a simple addition problem, 25 plus 45 equals 50. 25 grams of A, 45 grams of B equals 50 grams of D plus whatever that amount of C is. So we're going to do a simple addition. So I'm going to add the stuff together on the left first. 25 plus 45 is 70. So 70 equals 50 grams plus whatever my question mark is, whatever it is I'm looking for, my C. So I'm going to subtract 50 grams from both sides so that I can get the question mark by itself. And that gives me 20 grams is how much of my product C is made. So what that tells me is if I have 25 grams plus 45 grams, that's 70. So 50 plus 20 also equals 70. The mass before and the mass after have to be the same. That is kind of the entire point of the law of conservation of mass. So when we're dealing with chemical equations and chemical reactions, the one thing you need to make sure you understand, though, is whether or not a chemical reaction took place. Okay? The law of conservation of mass applies to chemical reactions. So how do we know if a chemical reaction took place? We have evidences. But these are our 5 evidences of chemical reaction. The first is an unexpected color change. Now, when we say unexpected, it's not what you would intend to think. So if I have something that is blue and something that is yellow, and I mix them together and I get green, you expect to get green when you mix blue and yellow together. And so that would be an expected color change. An unexpected color change would be something a little bit different.
So when we say an unexpected color change, we mean a color change that you would not normally think of getting. For example, this is silver nitrate. It's a nice little clear liquid. This is potassium iodide, also a nice little clear liquid. And when we mix them together in this test tube, you get something that is not a nice little clear liquid. It's a little pale yellow. So that is an unexpected color change.
The second evidence of a chemical reaction is the production of a gas. When I combine two things together and I produce a gas that was not there before, then we have ourselves a chemical reaction. It is the production of a gas. The best way to know that a gas took place or is being produced is when you recognize or notice bubbles.
So in this reaction we have sodium bicarbonate, a nice white powder, and acetic acid, a nice clear liquid. I'm going to mix them together, and when that happens you get all of these lovely bubbles, which is the product of carbon dioxide being produced and causing it to foam up and bubble. So you're having a gas be produced from your reaction.
Production of a light is another evidence of a chemical reaction. So when we have something that's just here and then all of a sudden light is produced, well, there you go, production of light. A good example of that would be a glow stick. You crack it, you mix the light, and light is produced. And then you have other reactions that also produce light.
All right, so this is a strip of magnesium, and we're going to set it on fire in the heat, and it's going to start reacting with the oxygen in the air, and as it reacts, it's obviously producing a whole lot of light.
A temperature change, whether the thing gets hot or gets cold, its temperature is changing. So when you do some chemical reactions, the temperature will change. And when the temperature changes, you have yourself an evidence of a chemical reaction.
All right, so for temperature change, in here I have an ice pack. There are two different chemicals in here that are being separated by a seal. And so we have the temperature that is happening right now, the before, and then after I break the seal and mix up the chemicals, we will have a temperature after. If I can break the seal. And we can see that drastic change in temperature.
The last evidence of a chemical reaction is the production of a precipitate. A precipitate is a solid, which is an undissolved product from two or more chemicals that were dissolved in solution. So you started with two chemicals that were dissolved, they were both soluble, and you end up with something that is insoluble, and so you have yourself a precipitate.
All right, so when we are talking about the evidences of a chemical reaction, one is a precipitate. So I have here two chemicals that are dissolved in water. They're both what we call aqueous, being dissolved in water. So I'm going to mix them together, and a precipitate is a product that is not soluble, and so you can see that it makes a nice white powder that does not dissolve. And eventually it will all settle to the bottom of this beaker. It falls down like rain, and that's why we call it a precipitate. It precipitates out, and that is a precipitate.
Now, these are evidences of chemical reactions and the law of conservation of mass. So make sure you understand that when a chemical reaction takes place, the mass, the total mass of the system stays the same. Your mass of your reactants and your mass of your products are going to be equal. So you need to make sure that you always consider that. It makes a really big difference on why we do a lot of the stuff we do in chemistry. And what we're going to be dealing with for the next couple of weeks and a couple of videos is dealing with how we account for this law of conservation of mass in chemistry. And so when you're dealing with chemical reactions, you need to recognize that a chemical reaction has taken place by looking at those evidences, and then know that the total mass before and the total mass after are the same. So That's it for this video. Thanks for watching. Have a day.